Hello and welcome back to the Hyperthesis episode 30. We actually made it to 30 episodes, which is really nice. And
Woo!
today we have a bunch of interesting things to talk about. Some fun research that, might be intriguing. So, my name is Pheely.
I'm Patrick.
And I'm Liam.
All right. So here we are, back to the hypothesis. So for the intro topics, I actually found something very interesting. Literally last night, I was browsing the internet as usual, and I found there's a new movie trailer for Oppenheimer. For those who don't know, Oppenheimer is the head of the project of the Manhattan Project, which we just discussed, I think, last episode or two, about the development of nuclear power and atomic bombs. And there's a movie that's going to be directed by Christopher Nolan about it. So I would like to see how scientifically accurate it is. Actually, that's not why I'm going to go see it, because I'm going to go see it for my own entertainment. But knowing the background and who are there and what they do, some of the theories behind it, are going to make viewing more, what's called critical, or I wouldn't say more enjoyable even. I would say I'll be more critical of the film because, we know some of these stuff and we know what they should look like and what they would do and how much effort, like how they portray physicists.
I actually really like watching movies or documentaries that I already know about. Like there's that Stephen Hawking movie. It's like The Theory of Everything or whatever. And I already knew a lot of that going into it, but I don't know. I enjoyed it. I was like, yeah, my boy.
Yeah, I'll be curious to see if Christopher Nolan adds any unexpected twists. I know he always likes to play with time, so the one thought in my head is the nuclear bomb going to go off and everyone's transported back in time or something like that? Spoiler for nuclear bombs going off if you don't know anything about the Manhattan Project.
It's gonna be hilarious. It's like, oh, the nuclear bomb went off. We just like, turn into a cartoon or something, just completely off the rail. Like just to throw all the viewers. But I don't think he would do that.
It's like some Into the Spider-Verse stuff, but for Oppenheimer.
Yeah, exactly. So Cillian Murphy stars in it, so that's gonna be interesting because last I watched him was in like Peaky Blinders, which has like a thick Birmingham accent. I think Birmingham, and he, now is doing the American accent, which he himself is British, and usually British actors are quite well versed in American accent because when you think about it, like you don't really sing, they don't really sing in British. It's a little bit, but it's like they sound American singers when they sing.
Yeah, I wonder why that is.
Just the way it's pronounced, I guess, like words. Phonetically, American is closer to phonetic, well, without the, what's the word? Intonation of inflection of each word. So how things are arranged. Well, I'm not a linguist, so I have no idea. Maybe, if anyone want to correct me, feel free. I'm up for grabs. So, but why I mentioned about this movie is that it relates to the introtopic topic that we kind of prepare-ish. And what we have read about was sent to us by one of our friend, Catherine. Thank you very much. And it's really interesting because it relates to those time when they, do the Manhattan Project, the 30s and 40s to now. And one of the main key point is that the scientific discovery then seemed to be many more, and there's more wow factor. There's more pivotal, some might argue, than now that there are like more like a bunch of smaller scientific discoveries, and they talk about how culture has changed and how things has been different now, what we look for in researcher then and now, and they compare a bunch of stuff. So let's talk a little bit about that.
Yeah, so just to take you through the article, first of all, thank you, Kat, for submitting it. But this was published in the Proceedings of the National Academy of Sciences, or PNAS.
Oh, wait a minute.
I just
Okay.
heard it. That's my
All
first
right.
time
All
saying
right.
it out loud. Oh
For
goodness.
penis.
Yeah.
Yeah. It's like that the what's it called? That project our friend Heather was working on. They have this this program that's the abbreviation for it is edibles or something like that. It's like who comes up with these?
Yeah, in particle physics, like WIMPs and stuff, like weakly interacting massive particles. It's just
The-
called.
Then there's machos. Anyway, yeah.
Anyway, so the Proceedings of the National Academy of Sciences. Sorry, I will not say the acronym. But this article it essentially argues that for the past 50 years of scientific research, there hasn't been a lot of innovation in terms of fundamental breakthroughs, or not nearly as much as the previous 50 years. So they look at the time frame from 1915 to 1965, and then 1965 to 2015. And they don't really provide a lot of examples or I guess, quantitative data. But they argue that in fields like biology and medicine and climate, among many others, things are perceived to not be simplifiable. So they're unsimplifiable, as they word it. And instead, they rely on simulations and the collection of a lot of data that just doesn't allow for these large breakthroughs. Now, they also say that with the singularity for AI coming, maybe in the next couple of decades, we might like get to the point where we're having constant breakthroughs, but they say that there are underlying issues related to big data science.
Well, I actually disagree quite a bit with the article because to me it's too reductive of efforts in terms of scientific discovery. What do you mean by huge scientific breakthrough? A lot of those are perpetuated by media, right? What is a great breakthrough? Like, Einstein, when he first came out with theory of relativity, it was like nobody really cared that much because, like, well, nobody believed it, and maybe it is the biggest thing. And now that we know it's kind of a big deal, right? And we, as in history, now that we have a better foundation of things, what we found are more complicated. I don't think it takes away from it being a smaller breakthrough. To me, there are much bigger breakthroughs. They just have a harder time judging it because the complexity of it is like part of it said, it's not really reducible to this simple form that this easily discussed. And to me, that a bigger breakthrough that we were being able to understand this with more people even. Like back then, it was exclusive to a certain group of people who are really privileged and really intelligent and smart to be able to access this information. But now anyone can look it up and be able to join that.
Yeah, it's like it's very kind of what do you call a big breakthrough? Because I guess when I think of like big breakthroughs, at least in physics, it's like quantum mechanics and general relativity, right? Because you had to change everything about the way we thought about nature to kind of get those. But in principle, now that we understand quantum mechanics and general relativity, it's like, oh well, the rest of it is just like kind of fleshing out those two topics. I mean, that's debatable, of course, because we're trying to make the two topics work together, and that's a whole ordeal. But there are these like massive changes in thought where you can argue that like maybe every other discovery since then has just been kind of like a subdivision of these two fields, at least in quantum mechanics and like general relativity. Those are just like two examples, but I don't know, like yeah, what do you call a big discovery? Because you can argue that like even something that seems really trivial could really change the way you think about things. Because it's like quantum mechanics, it's just like, oh, things are discretized, and it's like, oh my god, like there's more to it than that. But like essentially, that's all that changes. And I guess you have like superpositions and things, but that's all kind of like that comes out of the fact that they're discretized, I guess.
I mean, this article, it doesn't, I guess, focus too much on physics. Like, of course, it mentions Einstein, but it also says that in the 50s, we were able to figure out DNA and the code for life. And it wasn't just, in fact, they use very few examples, but talk more broadly about science. And There there are a couple arguments they make that why there aren't these major breakthroughs or paradigm shifting breakthroughs, if you will, like quantum mechanics or like relativity. So their first reason is the prevalence of being online, which is especially true for younger scientists.
Oh, my hypothesis, all right? It has to do with length scales. You can only zoom in on things so much before you see everything. So that's my guess is that like science since the beginning of the 1900s, it's like we get better like tools, better microscopes. We can zoom in on cells and on DNA and on molecules and on atoms, and you get zoomed in and zoomed in and zoomed in, and you learn more about these things.
Oh, let me play devil's advocate for a bit. Because like an analogy that I like to think about these is that, in music or art, when drumming, example, it's the most major breakthrough. Oh, it's the first guy who picked up a stick and hit a piece of leather. Is that the most breakthrough? Or is the guy who maybe invent jazz? Or is the bigger breakthrough who actually take jazz to the next level? So who could say which one is the bigger breakthrough? Maybe the first one is simpler, but does that mean the guy who reinvent jazz or create blues from things, from hitting drums or instruments, are less important than figuring out like first how to hit the drum? To me, in physics, well, you can figure out. I'm not saying those are simple things. There are actually like a very difficult challenge to figure out in the first place. But I don't think we should take away from the fact that like there's something great and amazing about this new, smaller, some arguably smaller breakthroughs. To me, they're bigger breakthroughs because it requires more complicated, complex thoughts and weaving around these ideas. At least in my opinion, these are bigger breakthroughs, even though might not have as much impact to basically like in social media or in terms of like what's awareness of it. But to me, there are bigger breakthroughs.
Yeah, that's a good argument actually. I like that. I like that idea. And the way you do science is you typically start off with like the simpler case, right? And then you build upon that. So all these like ideas that have come from a long time ago, we've been building upon them for years and years and years to the point where they're so like complex. Like the universe is complicated, right? Like you think of yourself, and it's just there's so much going into like your existence, let alone like a single hydrogen atom. Like single hydrogen atom's pretty complicated. Now look at you. You're a lot of different particles. You're a lot of these biological systems in play. It's a miracle we even exist, right? So I don't know. I think these discoveries, the science that people are doing now, even though it's been built upon for so long, that they seem like these little trivial like kind of discoveries, but they're so complicated and so hard to understand compared to what people were doing like 100 years ago. And I think that's not just physics. I think that's everything, right? Like it is very impressive, and that's why you need these huge teams of researchers. You need these giant particle colliders, and it's very hard to become like an Einstein these days. You can't just sit down and be like, oh, I have this weird idea, and then a whole field of physics comes out of it.
So it's interesting in this article because it doesn't really go into, I guess, the increasing complexity of the questions that we're asking. And they kind of missed that in the article itself, talking about that they recognize that there are more complex systems, but they argue that the way that we deal with those is not the correct method. So along with their first point being that we're spending too much time online and so can't think as deeply about these issues, which I think is just far off the mark. They have a couple other reasons.
Yeah, well, I think one of them was that people who make breakthroughs or big scientific discovery tend to be more antisocial, which could be. Well, I mean, I think that's statistically true. People that are more interested in theories and things like this are usually less interested in people. Like we just don't care as much about having, good. Well, I would say good interaction, but I mean, I have as much social life as people, let's say in humanities or people interested in people. And you can see a lot actually among my peers, my colleagues, and we can see like some of us, like me, I like to keep to myself from time to time, right? But I feel like that's overgeneralization, and And to me, it's like, is that an impetus of what you want to? Is that a message you want to tell people who want to go into your field? That's like, oh, you gotta be antisocial to be successful. Most people are successful are antisocial, or there are a lot of bad consequences coming to being good, being great in the field. I don't think that's the message that should be sent. It should be like, here, this is the best version of being the best physicist, and this is the idea. It shouldn't be antisocial. It should have a balanced social life and whatnot. Maybe that's too much to ask. Who knows? But at least for young people, I think there's a better motivation.
I do want to return to that, but just with the point that they made, they said there were only 2 major discoveries, and those were made by people who preferred solitude. Now, these were more so mathematical, but I think they completely missed one of the largest discoveries within this century, which was the discovery of the Higgs boson. And that depended on thousands of people to be able to make that discovery that the Higgs boson actually exists. Now, it's based on theory from Higgs and just a couple other theoreticians, but the discovery itself and proving that that was real, that's a massive breakthrough, which they've neglected to mention here.
I mean, it's a big breakthrough, but like, as far as the Earth is concerned, is it really that big of a breakthrough? Like from a physics point of view, yeah, that's huge. But like, is it really changing our lives?
Well, let me give you another example. Then, like Einstein, Niels Bohr, those people during the time, they correspond all the time, through letters and stuff. It's not like they just want to be alone, try to figure out by themselves. There are a lot of collaboration going on, even in those times when it was really difficult to do, and they have to take effort try to do this. And it's not someone's idea in their head alone. There are, and as you go to research, you realize the value of bouncing ideas off people.
And that's something that they mention as their second reason why there haven't been as many breakthroughs. And it's, quote, a veritable epidemic of communication, end quote, where the threshold for interacting with people is extremely low, and therefore it's become too easy to collaborate, which takes away individual directions in research and instead sets us all on similar paths, no matter what our field is, and that science nowadays is defined by big projects instead of these big ideas, which I agree with parts of those, in that sometimes too much communication can be harmful. For example, in my master's, I was in 8 or 9 meetings a week, which when are you supposed to get work done when you're always trying to present, and in meetings, presenting your results that you're supposed to be getting sometime? And if anything, I think that leads to a toxic environment where you're overworked. But I kind of agree that communication can be taken too far, but there is definitely benefits to being able to easily communicate and ask questions when needed.
Yeah, I see what like. I agree with that too. Too much. I don't know. I spend a lot of my time at my job like emailing people, and it gets pretty annoying sometimes. Because it's like it could be more efficient. Like I shouldn't need to always be in contact with people. And like what you said, if you end up collaborating with other people, you end up having to meet them like all the time. And if they're in different time zones, it's a huge hassle and like stuff like that.
Yeah, and to me, it's not just in science industry. And when you have seen that in many private sector and companies try to reduce meeting time, reduce this conferences call, or put effort to like, oh, just have 10-minute check in, 1 minute check in instead. So it's culturally and historically, it's not just us, right? Because this information age affected every single one of us. And the way people work has changed. I don't think we have found a stable phase yet where things are going smooth. We are still figuring it out, and it's fine that we start from not having any communication to having little. Now we're having too much, so we have to tune down a little bit. Hopefully, we'll find a balance soon. I know some groups they try to find a good balance between meetings, work meetings, and personal life and work and personal, like intellectual conquest. So yeah.
Especially with COVID, right? Like because of COVID, everything became a lot easier to do online, like Zoom meetings, like like all these platforms you can use. Made it very easy to communicate online.
Yeah, remember when people has to fly in, to discuss a bunch of stuff and to collaborate, and now it's like, oh, let's hop over on Zoom instead. Like, I would rather, if financially allowed, just go to the place and have those kind of experience. But people tend to differ.
Yeah. It has its positives and negatives. But anyway, back to this article. Or is there more?
Yeah, so there's one more reason that they state why there aren't these big fundamental discoveries happening anymore, and that's a shift in job opportunities and how jobs in academics and in research have been changing since the middle of the 20th century. And so you have these big companies like Google and Microsoft that are pushing innovation, but they aren't really pushing fundamental research. Like, for example, the Bell Labs is what they used in the article. And this also kind of relates to the publish or perish mentality that has definitely infiltrated and taken over academia, where it's the idea that you have to keep publishing, and the more you publish, and especially in more reputable journals, the better you look. So if you have 10 publications a year, you're more likely to get hired than someone who has 5 a year. Again, given that you have decent quality journals. And this means that you're just thinking about small ideas to increase things incrementally instead of having deep thinking with these profound ideas that might not, like you might publish maybe once every couple years with these big ideas instead of publishing many times a year with these small ideas.
Yeah, I actually agree with that part because in academy in general too, now the purpose, at least what's being presented to us as a solution to have a good career, or like guide have a good careers, like have good publications, or some people care about H index, which is like an index to judge a paper, and there's so much measurement or like examination of our lives that it's like, well, if you compare to before when not many people has opportunities to do this, and people who are actually doing scientific research on the cutting edge level are actually the, like, it's not as competitive, we'll say. Like, people are free to explore more, and they don't, like, now people feel pressure to publish something, and you can imagine scientific process can take 10 15 years to develop in our head. It's not quick. So that pressure of publishing a lot is real, and it's tough sometimes. Oh, you want to have a good career, and everyone else telling you to publish, and but you don't fully form your ideas. You haven't done that yet in 5 years. I mean, 5 years is, in a sense, a short time to solve this millions of billions years long problem from the universe.
Yeah, it's also like I don't know. There's this huge pressure to publish, and there's also like people are afraid to publish kind of bold ideas because you get these like peer reviewed journals, which is good. You should have peer reviewed journals. But I see so often people will like try and publish something and they get feedback from the journal, and it'll be like, oh, this idea is too weird and doesn't like make sense. It's like, well, I mean, if it's mathematically correct, like what's wrong with it? Like, string theory is very weird, and we can't test it, unfortunately, which is its only, if you could test it, then wonderful, like wonderful idea. But I don't know. Like I know I like yeah, it's hard to explain, but it's you get people who are afraid to publish these bold ideas because they're like, oh well, it goes against the norm, and my colleagues will, like crap on me for it and stuff like that. Because I see that all the time. People present at conferences and they have this like wild idea that's pretty cool, but also kind of out there. And everyone in the audience is just like, oh, that's a dumb idea. It doesn't make sense. And it's like, well, if the physics and math tells you it makes sense, then something's going on.
Yeah, and that's the point the article makes is that peer review processes like submitting a paper to a journal or applying for funding. The funding agencies aren't looking for these wild new ideas. They're looking for something that I guess is a safer investment. And they talk about how younger scientists don't have the freedom that they did back in like the 70s and 80s. Well, and even before that, And so it was possible to take these longer shots and receive funding for them, whereas now you might tank your career if you don't if you don't deal with this. And they also talk about how with the discoveries that people are making and making these minor publications, instead of thinking about like these complex relationships in simplified terms, instead they're looking at just small statistical significances within data. And therefore, big data is, I guess, inhibiting these fundamental discoveries because we're just looking for statistical significance instead of underlying theory.
Yeah, it's very interesting how, like, in scientific research, and I always come at it from a physics point of view. Maybe I should be more broad, but you always you're always told like, oh, like these super creative guys change the field. But then your entire career, like your undergrad, my master's, my PhD, you're always to like go down the path that we know. You're never taught to like you're like, oh, you got to think of it this way, only this way. Any other way is wrong, and stuff like that. And it's like, well, I mean, that's what we thought about Newton's theories. We're like, well, Newton's right, nothing's wrong, and then suddenly, boom, there's all these other things. So, and I find that getting enforced quite a bit. I don't know. I've thought about this before a little bit.
Yeah, I think one of the things they mentioned too is that, almost like our work and stuff needs to be visible to have a good career, but they claim that deep thinking is not. Well, maybe sometimes deep thinking is not visible, but I feel like, at least to me, is deep thinking involve a lot of discussion, actually. I mean, maybe that's part of invisible. I lose sleep many nights just thinking about certain topics that, that intrigue me or really confuse me. And then, maybe a couple of days later, I would call my friend or talk to my supervisor or my colleagues about these deep ideas I had. May not be a scientific breakthrough, maybe just to realign my understanding, to have another perspective. And deep thinking, people, I feel like the idea when I say the word deep thinking, people think of that, what was that statue, Michelangelo,
The thinker.
maybe that's some part of that. There's a lot of that in my thinking, but the thing that really kind of crystallized my thinking is to discuss it, and to me that is very visible. Maybe a smaller part of it. So yeah, I mean, people who spend too much time thinking, I think that's a problem too. There are other parts in life that facilitate your understanding of the physical world. So maybe that's one of my pillars why I try to do other things rather than physics, to actually get idea what life is, rather than just the physical modeling and description of the world.
Yeah, it's the more I get into physics, the more I'm interested in other things. 'Cause it's like when I started this career path, it was very much like, oh, I don't care about other things, and now I'm like, oh, these other things are the real. This is the really interesting stuff, actually. And it's also when collaborating with other people, there's this whole like Richard Feynman thing where the way he practiced, I guess, was that he would try and he's like, or was it Einstein? I can't remember, but someone there's this quote basically. It's like if you can't explain it to a child, then you don't understand it well enough. And I very much try and kind of, if I can't explain it to people who aren't in my field, then what's the point? Like it's too complicated. You need to be able to. There's certain levels you need to be able to describe it to. Like you have to describe your research to your target audience. So if you're with experts, you should be able to get into like the nitty gritty. But if you're with people who aren't experts, like there's no point in getting into the nitty gritty. Just you need to simplify things. And I find when discussing research with other people, like you're saying, Feel like you've called me before and proposed things or brought up topics, and I love that. It's awesome. And I think you need to do that you need to talk to people who aren't in your research area to better understand things. I don't know. It's cool. Maybe we should move topics though. Maybe the main topic will be a bit shorter today, but I think we should move on to it.
Yeah, just to wrap up, the final thoughts from the article are that we need to change our fundamental thinking of how science is done and kind of revert back to the old days where we focus on quality instead of quantity. So being allowed to take that time. and that governments and funding agencies and universities need to change the way in which they distribute funding to allow for that quality instead of quantity. And their final argument is that by spending less time taking professional selfies, as they call them, or small, I guess, light, not in-depth thoughts like light articles and getting more of them out there, and instead we should focus on larger projects with fewer people, we might get back to that age of fundamental breakthroughs.
Yeah, I half agree with the article and I half disagree, but I agree with that point. I even find myself kind of, whenever you hear someone's research, the first question you ask is, so why should I care, right? But there's nothing wrong with trying to understand something that we don't understand just for the sake of understanding. There's nothing wrong with researching something just for curiosity's sake, in my opinion. So a lot of good stuff comes from that. And yeah, these granting agencies and people in general, they have a hard time understanding that. Like, you present your research and they're like, so how's it going to help my life? It's like, well, I don't know. It's just interesting. Like, it may be in the future. Who knows?
My wrap-up statement for that is, when I read these articles, I always usually against like this "make this great again" like it used to be kind of argument. And you heard some of that in popular media about make something great again, right? That is it's, to me, that's anti-development a little bit. I think things flows evolve to something else, and people try to go back to the old times, and it's usually don't end up well. It's either end up with bloodshed or or systematic failure of things. So I would just say to this that we should strive to find something that's better or improve things are better, not to revert back. Look at the past as a goal. We should look at it as history that has lessons, has good part from it, but it shouldn't be a goal to revert back to the 1920s. That's one. That's just my thought, my ending thought on it. All right. So for today, we have our main topic on lightning and laser, which sounds like they're not related, but they are quite so, because light and lightning, light lasers, light. Or Liam knows more about it. So these are actually very recent research done. I actually, when Liam put this topic, I was like, I read about this somewhere. I saw a magazine with the picture of like a photograph of like this facility in the Swiss mountain and stuff. So yeah, I think I've seen it. I've read part of it, but I don't think I know that much about the details. So I will let Liam take away.
All right. Well, this is we've kind of flipped the role of intro and main topic today, because it's been around like 30 minutes of our intro topic, and we'll have about 15 minutes for this topic. So
yeah, thank you, Kat.
Yeah, no, I don't mind. I like that topic. So I might skip over some details in this, but yeah, it's so I basically found this paper called "Laser Guided Lightning" in Nature Photonics, and I thought, oh well, that's interesting. So their team of researchers conducted some experiments in the Swiss mountains where they fired a high-powered laser, and they actually found that it could influence the trajectory of lightning strikes. So I thought that was kind of cool, and I'll get into that a little bit. So I guess, like, first of all, what is lightning? So we know at face value what lightning is. Like, you've probably seen it or heard thunder before. So imagine it's like raining out and there's some dark clouds, and suddenly for just a fraction of a second there's this big kind of bluish flash of light that occurs. Or you see this like kind of twisted, jagged bolt emanate down from the sky and hit the horizon or hit a tree, or I mean, hopefully it didn't hit close to you because those things are loud, but that's lightning, and the sound it produces is what you call thunder. So if you hear lightning, and if like you see lightning and then a few seconds later you hear this big rumbling, you saw the lightning because light travels really fast, so you could see it. But then thunder, the sound it emanated, takes a bit longer to get to you. You can actually kind of judge how far away lightning strikes based on its sound. You can count a few seconds and measure the speed of sound in air roughly, so you can do the math. Anyway, so lightning's this electromagnetic phenomenon, and it occurs in our atmosphere, and on the surface of the planet. So it can occur within the atmosphere itself, but typically when we think of lightning, we think of it happening between the clouds and between the Earth. It's an electrostatic discharge between them specifically. Turns out that the details. How do I describe this? Essentially, due to atmospheric stuff that I won't get into because I don't fully understand it. I'll give a little brief explanation, but what ends up happening is that you have electromagnetic charges. You have electric charges. Things have, so like an electron has an electric charge. Proton has a positive electric charge. Neutrons don't have an electric charge; they're neutral. So things can have charge. It's like, on a really dry day, especially in my apartment right now. Like anytime I get out of bed, I've kind of rubbed against the blanket or the mattress, and I touch a door handle, and I get shocked. Kind of the same idea is that these clouds, there's all these molecules whirling around, and they bump against each other and brush against each other, and some of them exchange charges. So what ends up happening is that in these kind of thunder clouds, the bottom of the cloud will get like a net positive or negative charge due to particles falling, and the top part of the cloud will get a net positive or negative charge due to charges rising, and these falling and negative things bump into each other and exchange charges. So the Earth will have a charge as well, a net charge. And what causes lightning is that the bottom of these clouds have they'll gather a very large positive or negative charge relative to the Earth, and they'll want to discharge to neutralize that charge. So that's a very like hand wavy, rushed explanation as what lightning is. And there's excuse me, there's different kinds of lightning. So like the bottom of the cloud can have a positive charge or a negative charge, and each kind is slightly different. One of them is more energetic, I think. I'm not 100% sure on that. But so these typical lightning flashes, they form, essentially what they do is they form this electrically conducting plasma through the air, which causes this instantaneous release of energy. And it's a good amount of energy. It's about like a gigajoule, which is pretty big. And so a lightning flash or strike can produce a wide range of electromagnetic radiation. So it can create visible light because we see it. And the heat that created from it causes these electrons in the air to move. So that's what emits them. So it can emit black body radiation or other forms as well.
Well, I like to point out that like these lightning that happens also because like there are potential difference basically between the cloud and the ground, right? And the air is fluctuating, there's wind, there's stuff, so the conductivity is changed, the resistance changed basically. And somehow, if the condition is right, the resistance is low enough, maybe from the wind and from things, and the potential difference is high enough, it's gonna create lightning. And well, I'm gonna spoil a little bit. Then my understanding of lightning rod is to facilitate on the ground that thin, smaller pathway that's more preferable, just a little more preferable. So most of the lightning would go there. But my guess for the laser is you can create basically a bridge from the ground to the sky, that basically a very preferable pathway for lightning. It's like, when you short circuiting things, right? You put a wire that's like ideally would have zero resistance, which is not true. Have very low resistance, and put a wire in, so all the current would go through the wire. So my guess, and I think I might have read it somewhere, is that use laser to provide that kind of pathway to the sky to short circuit the atmosphere, basically.
Yeah, you're right. That's exactly the mechanism behind it. So like if you have this lightning cloud, whizzing over land or something, the lightning discharge, it wants to discharge because you have this potential difference, and potential differences they want to kind of neutralize. The charges want to travel and balance out. Things like to be in equilibrium. And it always wants to take the path of least resistance. So air is not conductive at all. Air is not electrically conductive. Well, it is, but it's very, very low conductivity. So for this lightning strike to occur, it's like you need a pretty big charge gradient for it to actually go through the air. So that's why lightning tends to hit things that are wet, because water is a better conductor. It tends to hit metal things like big metal rods or telephone poles because metal's conductive. And it tends to take the shortest path. So like it'll hit trees and telephone wires and things like that, because those are short paths. And so it's how do you protect against lightning? And that's with lightning rods. So lightning rods, you've probably seen them without realizing it, but the idea is that like it's just a big metal pole that's attached to the ground. So lightning will preferably hit that instead of a building. And the current will go down it into the ground, and then they'll neutralize. typically they're not too big, but like if you look carefully, you can see on certain buildings they have these little like metal things that are maybe like half a foot or a foot tall that stick out of their corners, and those are lightning rods. So this came from the idea. This came from like Benjamin Franklin actually, with his key on a kite experiment, where he had his kite flying in the air with a piece of metal on it, and it got struck with lightning, and it like traveled down the wire to him. I don't know the history if that's even correct. It's like the apple on Newton's head thing, right? Like, is that actually what happened? I'm not sure. But so they call these things these are Franklin lightning rods, because it's a really old idea from like the 1800s, and we still use it today. Um, some potential issues with your typical metal lightning though is that you put them on a building and they don't guarantee that the lightning's going to hit them. There's just a really good chance it will instead of other buildings nearby. So they have this kind of like effective range of protection, whereas like the further away you get, the worse the protection gets, I think. And it's metal, so you have to constantly. I mean, I don't know how often you have to do this, but metal degrades. Maybe you have to check it in on them. Maybe weather damages them. So this laser guided lightning is kind of like, it's an interesting idea. So the way it works is basically, but yeah, like you said, if you fire a laser up into the clouds, you create this region of higher conductivity. So the laser itself is acting like a lightning rod. And what is the physics of that? So this laser-based lightning guidance, it was first proposed in 1974, and there was experiments done in the lab to confirm it. However, doing it in nature has been kind of a challenge because it's very hard to predict lightning, it turns out. So you need to go somewhere with lots of lightning, and a lot of tests that people have tried are very unlucky, and you need a large amount of data, and it's hard to get that from lightning because you got to predict it. So what these researchers did is that they went to a Swiss mountain. I forget the exact name of it. And there's this tower. There's already a tower on this mountain. I wonder if I can find the name of it. It's like Santis Mountain, or something like that. Santis.
Saintis Mountain.
There you go. So to increase the chance of this laser-guided lightning experiment, they went and they placed all their sensors at this mountain because there's this big tower on there already that gets struck like 100 times or so per year by lightning. So there's already all these sensors in place from other researchers and data collectors that can actually measure properties of lightning as it strikes the tower. And 100 times a year, that's a lot. But for a scientific experiment, that's not very often. Like imagine you're sitting there at this tower for a year straight, and like these 100 strikes, it's not like one comes every so many days. And imagine they kind of hit in like bulk, whereas like 1 week you might get a bunch of strikes, and you don't get many for a while, and then suddenly you get a bunch more. So big problem with this experiment was being at the right place at the right time and having your equipment ready to go at the right time. So they conducted this in 2021. Yeah, so they had this laser that they used, and what they did is they didn't actually use the laser itself as a lightning rod. This is like a preliminary step to more future experiments, but they have a lightning rod already existing, like a metal lightning rod on the top of the tower. What they did is they kind of fired the laser past it, just past the tip of it, so it kind of like glances the top of the metal lightning rod. And their goal was to show that you can actually extend the effective range of this lightning rod with the laser. So if the lightning rod's only like a meter tall, say, by firing the laser just past the tip of it, you can make it 50 meters taller or something like that. So they fired this very intense laser, and the focusing of this laser, yeah. So the way the laser worked, it was so intense, and it was through this process called filamentation. So the laser, as it goes through the air, through the refractive index of the air, somehow it self-focuses through their technique. I don't know the exact details. So you reach this point where it's highly focused, and the focusing effects kind of become in equilibrium with the dispersion effects due to air. You get this actually pretty intense laser, and what it does is it ionizes the air that it travels through, so it increases its energy state. It heats it up a bunch, and this causes oxygen molecules around the laser to kind of shoot out away from it. So you get this region of lower density air, which actually somehow increases the conductance of the air that the laser is going through. Although I don't fully understand how that works.
I think in this case, the air is heated by the laser because it will interact with the infrared beam from the laser. And this will heat it, causing a lower density, so easier path for the lightning to get through. And it can also ionize the air. so it can actually break those electrons and from the atoms and create ionized air, which is more electrically favorable
Right,
than just
right.
regular plain air.
Yeah, so what's cool about this experiment too is that, I mean, if you want to build a lightning rod, you can only build them so tall, right? Before they start to become, you start to have like structural problems. Like, maybe the Eiffel Tower is a giant lightning rod, but that's a pretty big, expensive lightning rod kind of thing, right? Most lightning rods are only tiny on top of buildings. So the idea of the laser is like, oh my god, I could make like a kilometer tall lightning rod with a sufficiently intense laser. And the other cool, so you can actually, the idea behind it is that you could induce lightning. So you could create this really preferable path for the lightning to take and get the lightning to fire off long before it could enter like a city or a town or something like that. Or, for example, if you know a really bad storm is coming, instead of having like hundreds and hundreds of little tiny metal lightning rods everywhere, you could just have a really, really tall one in the middle of the city or like near the edge of the city or something like that. And you can also, they mention it in their paper. I don't know how, but they say that you can actually tune where in the laser's path your region of high conductivity it is. So you can actually create, if you have a powerful enough laser you could shoot into the clouds, you could create like kind of a path between clouds for lightning to discharge between the clouds themselves so it wouldn't actually hit the ground. I thought that was kind of neat, although I don't really know how that works. But anyway, in this experiment, they were up in these. I think they're still doing more stuff currently, or in the future they plan to. But they managed to record 14 lightning strikes, and 6 of which they had the laser activated for, so they could compare the data with no laser to the data with the laser. And what they actually saw is that they extended the effective height of this lightning rod by about 50 meters, which is a pretty big distance to extend the lightning rod. And they got some really nice pictures where you can see the lightning coming down and then kind of aligning with the laser and then traveling down exactly to the metal lightning rod. So this is the first step. It's kind of like, okay, maybe that's not super impressive, but I think that is impressive. I think that's very cool, and it's kind of like it's like a baby step to kind of future application of it.
Yeah, that's really interesting, but I'm just curious the effectiveness for example, for living in a city, the effectiveness of having this very high power laser, say reaching all the way into the clouds, a kilometer or two up, versus just buying a little bit of steel and some copper wire and just running it from the top of the building down. Like, it's certainly a very novel idea and very interesting, and it could very well be very useful in very stormy places. But to me, what's the benefit, especially cost wise, over a simple piece of metal on a
Yeah,
building?
that I don't know the answer to. I don't know how much more efficient it is money wise, or like I guess you'd have to go look into like how lightning rods actually function in society. Like how often do you need to replace them? Once you put them there, are they good? If they get struck by lightning, do you have to like replace them or fix them? Or how often do they get damaged? What's the cost of the metals? I don't think they're anything too fancy. Like I think they're just some fairly typical metals that you put together in an alloy or something. But yeah, it's like how much benefit does this have?
And are these visible lasers or are they IR, UV? I- Am I like is there like m- the the reason I ask is because like imagine if it's a visible red laser. Like imagine what it would look like. Oh, it's gonna start raining. We're gonna have this gigantic beam look like some kind of overlord just sending stuff onto the sky and all the lightning just go through it. It's like what's going
Yeah, I
on in
think they're
life,
infrared
man?
lasers. Yeah, so one thing that the study had to do too is that there was an airport nearby. So anytime they had to fire up their laser, they had to like inform the airport and get permission so that they didn't accidentally like shoot down any. I say shoot down. I don't think it would have shot down the planes, but they didn't accidentally start lighting up a plane with their infrared laser. One idea that I thought was cool was, what if they don't really talk about this in the paper, but like, could you generate power from electricity? Could you, if there's a big lightning storm, could you fire this laser up, guide the lightning to like some kind of battery, and then charge batteries from it? I don't know. Maybe that's a cool idea, but maybe it costs more energy to run the laser. Or maybe while you're running the laser, you have it kind of like a feedback system where some of the lightning goes into charging the laser itself. I don't know.
Oh, it's easier said than done because well, it's all about current, right? Like charging, so it's not about voltage difference. And what the lightning provides voltage difference. But lightning came in a very like short pulses, and that's hard to
Mm,
harness. Like you want to charge in a slow, not slow, like in a stable manner, right? And these things that keep shooting really short pulses of very high energy, like in quickly, so that if you think of any capacitor response, like in an RC circuit, that's not gonna fly that
true.
well, right? It's gonna burn your capacitor. So, well, maybe there are other things that we can do to harness that, but to me, it's really hard. Like with anything, even mechanical, right? It's like, all right, try to store energy from rubber band like being stretched and released at you. It's really fast. It's hitting, and hitting, right? Like, well, how you capture that energy and transfer it. So, like, oh, you kind of have to slow it down to transfer it, or maybe get that lightning to shoot a ball to a higher place to store energy. Like there might be a way to store pulsed energy or like convert pulse energy to a more stable storage, but I have no idea. I'm not an expert in this. I'm sure there might be some way
Well,
to do it, but
here's a proposition then
no
is
idea.
that if you can induce if you can induce lightning in the clouds with a laser, you induce it long before it's gotten too powerful, like the powerful lightning strikes you see on Earth. Because if you can make this really long lightning rod, you can induce the lightning long before it's gotten this huge charge gradient. So maybe you can get like a lot lower energy kind of strikes from it. I don't know. Who knows?
Well, the problem with that is you have to create a very strong conductivity because what's the resistance between ground and sky? That's massive. So you need so much voltage difference to overcome
Hmm.
that, right? So if you want to create a really small current, so you have to
Yeah,
reduce the I don't know how many billion ohms between the sky and ground onto something that like remotely
gonna cost you a
accessible.
lot of energy to run that laser.
I mean, your best bet is probably just launching a balloon with a cable
Yeah, well,
tied
that's
to it
actually method
up into the
before
cloud.
this laser method. They were trying to. There's other researchers who were trying to find ways to induce, like in the past, induce lightning. And one method was that they had a little rocket, and they would fire it into the sky, and there'd be a wire connected to it. And they actually found that you could induce lightning if you could get it high enough into the cloud, with a charge gradient, it would travel down this metal wire. But the issue with that is that the rocket's toast the moment it hits. It just blows up. It's kind of like it's like a one-time lightning rod that you can induce lightning with. And then you get all these debris from the rocket falling down to the ground, and you got to clean it up. And it can be done with like kind of simple things like that. But the laser was like kind of the cleanest method. You just shoot the laser up, it hits, and then you turn the laser off, and it's like nothing happened. But I think you're always going to have to like fire the laser past a lightning rod because you don't want. I guess that's one issue maybe they had to think about is you don't want the lightning traveling down the laser into the laser itself. It'll destroy all your equipment. You want it to kind of veer off at this lightning rod before it hits the laser device itself. But anyway, I thought it was a pretty cool kind of concept. Again, I don't know like how practical or useful it is, but I think it's worth investigating because it could be. Like we talked about at the beginning of the episode, maybe it will be useful. And if not, then we've learned something.
Yeah. And if you happen to be an expert in lightning or in atmospheric sciences and can tell us a bit more about how lightning works, because I mean, from what I understand, it's still not entirely known, then you can contact us. We have a Gmail email account. So you can find us at hyperthesispodcast@gmail.com. We also have an Instagram where we post updates and some behind the scenes looks, as well as some memes, courtesy of Liam. So you can also contact us through a DM there, and feel free to like and comment on our posts. We also have a YouTube channel, so you can go ahead and listen to us on YouTube with excellent visual effects by Pheely. As for our podcast, you can listen anywhere that you find your podcast, whether it's Apple Podcast, Google Podcast, Amazon Music, or Spotify, along with many, many other different podcast stations. We are at the Hyperthesis pretty much everywhere. And yeah, we are based out of anchor.fm. So go ahead and listen, like, share, subscribe. Absolutely detonate that subscribe button. Whatever that means. I'm told that works. And also feel free to leave a review wherever you're listening to the podcast. We always want feedback, so send us a message, whatever way you prefer, even carrier pigeon, and we'll hopefully receive it.
They're extinct now,
Yeah,
sadly. Oh no.
for now.
That's another episode.
Anyway, just to wrap up the episode, we'll just briefly tell the story about something that affects us all, and which was, I guess, a big component of our last topic that we just discussed, and that's the atmosphere. So this isn't a story about a person or anything, but just how the atmosphere came to be and what it's made of. So the Earth formed about 4.5 billion years ago, along with the rest of the solar system. And during the formation of the solar system, things got quite hot and quite dense. Well, relatively dense. And as rocks collided together and crashed together, heating up with all the friction that occurred and the deformation that occurred, the Earth formed. Again, that's about 4.5 billion years ago, along with most of the other planets and the Sun. And during this formation period, the Earth had its first atmosphere, which really wasn't an atmosphere at that point. It was more just hydrogen that happened to be stuck in the gravity well of the Earth. So much like the other planets, especially the outer planets, the earliest atmosphere was composed mostly of hydrogen, but there were also some simple hydrides that were found in the atmosphere, such as water vapor, methane, and ammonia. These are also commonly found in the atmospheres of Jupiter and Saturn. So we know that our atmosphere kind of started out there. So it was most likely a lot thinner and definitely not breathable. But due to outgassing from volcanism, so a lot of gases were released from the inside of the Earth, along with heavy bombardment by many, many asteroids that just pummeled the Earth during its early days. Again, the solar system was still forming at this time. There was a lot of nitrogen and carbon dioxide that was released, along with some other inert gases. Now, a major portion of the carbon dioxide that was released dissolved in water and reacted with metals such as calcium and magnesium, which formed a lot of the carbonates that were deposited within the sediments. And so this is how we can gain an understanding of what the atmosphere was like around 3.8 billion years ago. Now, around 3.4 billion years ago, nitrogen formed a major part of the second atmosphere that was no longer mostly hydrogen, but became mostly nitrogen and carbon dioxide. Now, at this time, Earth was maintaining a warm climate. We're still not quite sure how. There's a lot of questions trying to be answered with the early Earth, especially since the sun's output was about 30% lower than it is today. However, the Earth was able to still stay warm, and because of this, we have an excellent geological record of processes that took place between the atmosphere and the rocks and water in that time. Now, with this warmth, meant that the Earth didn't really go through cold periods. It did go through possibly one glacial period about 2.4 billion years ago. But also at this time, an oxygen-rich atmosphere started to be developed. Now, in this case, this was the responsibility of life. So life on Earth had formed in the form of cyanobacteria, which led to the Great Oxygenation Event. So this is where carbon dioxide in the atmosphere started to be converted to oxygen through photosynthesis from the cyanobacteria. And this was also the start of the carbon cycle, where carbon was stored in the form of dead life, such as dead cyanobacteria, and then eventually sunk down in the oceans or wherever the bacteria was located, and it was then cycled. Now, there's still a lot of research going into this, but with the advent of an oxygen-rich atmosphere came the third atmosphere, which is the one that we still have today, where it consists of 21% oxygen, 78% nitrogen, and a whole lot of other trace gases. Now, Some of those trace gases include things like carbon dioxide, which is quite the prevalent problem, but only about 0.04% of the atmosphere, or just over 400 parts per million. On average, about 420 parts per million of CO2 is in the atmosphere, whereas actually we have more argon at very close to 1%. There's also neon, helium, and methane, as well as water vapor in the atmosphere, which ranges between 0 to 3%, depending on where you are. Now, with this third atmosphere, or the atmosphere that we know today, there are different layers to it that go anywhere from the surface of the Earth all the way to well over 100 kilometers. And we actually see traces of the atmosphere on the moon, including water vapor. So we know that the atmosphere doesn't really have a hard boundary, but we can definitely see some hard boundaries within it. So the layer that touches the Earth is the troposphere. Now, this is where all life that we know of exists. This is where planes tend to fly, and this is the thickest part of the atmosphere where we also get most of our weather, if not all of our weather. Now, it ranges from heights between 9 kilometers and 12 kilometers, depending on your latitude, because the atmosphere is actually a bit thinner at the poles, and it bulges out at the equator because of the fact that the Earth is spinning. Now, the troposphere, again, is relatively warm and so has liquid water, and is responsible for the weather that we get, including all the clouds that you can see, for example, when you look from space. Now, there are many variations in the troposphere's temperature, especially during the different seasons. So this is where all the interesting stuff happens. We won't get into a lot of that interesting stuff, but we'll have to do a meteorology episode. Now, right above the troposphere, with a fairly hard layer, is the stratosphere. Now, it's the second layer above Earth and lies around 12 kilometers or plus, all the way up to around 50 to 55 kilometers. Now, in this part of the atmosphere, at the top of the stratosphere is around 1/1000th the pressure at sea level. The stratosphere also contains the ozone layer, which is responsible for blocking UV rays that come from the sun and keeping us safe. You may have heard about the hole in the ozone layer, which is recovered quite well since the Montreal Protocol. But the stratosphere has a lot more stable conditions than the troposphere. It has a better temperature profile, so there's less variation within the temperature. And this means that there's less turbulence and less things happening there. So it's very rare to see really any effects from the stratosphere. However, we do see effects from the polar vortex, which partly does lie in the stratosphere. Again, that's a whole atmosphere episode, which we'll have to do. Now, above the stratosphere is the mesosphere. So mesosphere, or medium, or middle, is this third highest layer, which goes between about 50 kilometers and about 80 to 85 kilometers. Now, temperatures drop with increasing altitude here, and it is the coldest place on Earth and has an average temperature around negative 85 degrees Celsius, which is a little bit cold. Now, there's something known as the mesopause, which is kind of this layer within the mesosphere, where there's very little water vapor. And again, not too much happens within the mesosphere. Now, there are some exciting atmospheric events that happen there, but again, we won't get into that too much. And we haven't really been able to explore it. The only thing that really we're able to do with it is travel through it, such as in rockets. We also tend to send balloons that can pass through the mesosphere. Now, after the mesosphere is the thermosphere. Now, it's separated from the mesosphere, so it extends from the mesopause, which is the top of the mesosphere, all the way up to the thermopause. So it goes between 80 to 500 to 1,000 kilometers. Now you might be asking, there's the space station orbits at 400 kilometers. So it's actually passing through the atmosphere, and that's why it needs to be boosted every once in a while. But the thermosphere is named as such because it's hot. So the temperature of the thermosphere gradually increases and can go up to 1,500 degrees Celsius. However, the gas molecules are so far apart that temperature in this case doesn't have the same meaning as if you were to stick your hand into a 1,500 degrees Celsius oven. Now, it's also not very dense there, so things like the space station and other satellites can pass through it quite easily. Now, despite its very low density, there is a layer above it, which is the exosphere. Now, this is the outermost layer of the Earth's atmosphere, and it extends from the thermopause all the way to 10,000 kilometers and possibly past that. But at that point, it's hard to differentiate between the exosphere and the solar wind that comes from the sun. So this is mainly composed of very light atoms, like hydrogen and helium, and a little bit of oxygen and nitrogen and carbon dioxide. But again, this is very, very low density, and so there's not too much that happens there, aside from the aurora borealis and aurora australis. Now, those also happen in the thermosphere, where there's a bit higher density of particles, but it can happen in the exosphere as well. So that was a very brief look at the atmosphere. We'll have to get perhaps a special guest on to talk about it one day. But in the meantime, I can recommend the book Firmament by Simon Clark, who is, I guess, a social media influencer, but he's also a scientist who did his PhD in atmospheric physics. So I would recommend checking out that book because it has a lot of excellent information relating to the atmosphere. And Simon, if you're listening, please come on our show.
Simon, I've been watching the Yogs cast for the last 15 years of my life. That would be my dream, to get him on the show. There's these people in England who play video games who I've watched for a long time, and he does stuff with them sometimes. Anyway, side note.
All right, sounds good. Thank you, Patrick, for the story today. And, well, I guess we'll see you next week for more interesting stories.
Bye, everyone.
See ya.